Today, I'll warn you, is the Ides of March, so be careful. You never know what might happen to you today. And today we're going to start differentiation. Let's start with a gradient. Here we have a straight line, and here we have a bicycle who's going up the gradient. There's a person on the bicycle, and he's cycling up the gradient. Gradient is equal to the change in y divided by the change in x. Okay, so it's how high does it go, and I'm going to call that dy for a given distance in x, dx. And a positive gradient means that you're going uphill. Okay, so gradient m is equal to dy by dx. Okay, so that equation here, m equals dy by dx, is the same as this equation here, but I've just used an abbreviation that says what's going to, an abbreviation just to make it quicker to write. And if we had a gradient that's doing this, a gradient that's doing that, here's your bicycle, those are the forks that comes along there, there's the person, there's the head, and they're zooming downhill. Okay, and that's a negative gradient. Okay, so again, to find the gradient, we find the change in y, which is dy, we find the change in x, which is dx, and we've got dy by dx, which is the change in y from here to here is going to be a negative quantity, and the change in x is going to be a positive quantity, so that's going to give us a negative gradient. So that's okay as far as it goes, and we can calculate gradients of straight lines. Indeed, we were doing linear regression because it's easier to do that than any other kind of polynomial regression. But what happens if we've got a curve like this? Okay, if we've got a curve like that, how do I find the gradient at a point like this one here? Okay, what I have to do is, you can imagine the gradient at the bottom here is 0. Okay, and the gradient over on this side, oops, let's try that again. Yeah, the gradient there, m is greater than 0, that's to say it's positive, and the gradient here, the gradient there, is less than 0, so we've got a negative gradient over there. Okay, now the question is, how do we calculate these gradients? Because the gradient is always changing. That curve is always changing, so the gradient is always changing. So what we're going to do is to use something called differentiation, and the rules of differentiation are, is we take a term like x to the power of n. Okay, so to differentiate, we multiply by m, multiply by n, and then, so that's 1, and then 2, we reduce n by 1. Okay, so we have a variable n, we multiply, I have to spell that right, by n, and then we reduce it by 1. So if we want to take d by dx of x to the power of n, okay, that what happens there is we multiply by n, so we get n times x to the n, but then we reduce the n by 1, so it becomes n minus 1. Okay, so let's just say that again. We've got x to the n, and what we're going to do is we're going to multiply by n, so we take the n and multiply there, and then we reduce n by 1. So as an example, let's try x, oops, as an example, let's start with a simple thing like x squared, and if we differentiate that, d by dx of x squared, and that's going to equal 2, we multiply by n, and then we reduce n by 1, so that becomes 2 times x to the 1, you wouldn't bother writing the 1, but I've just written it just so it's clear that I've reduced 2 to 1. Okay, so that is how you differentiate. Now let's imagine what happens if you differentiate d by dx of x. What's going to happen now? Well, the coefficient, the exponent of x is actually x to the 1, isn't it? So we're going to multiply by 1, and then we're going to reduce the power by 1, so we're going to get x to the 0. And anything to the 0, apart from 0, is actually equal to 1, so that is going to equal 1, isn't it? Okay, and now let's imagine if we differentiate d by dx of 1. Okay, this is like 1 times x to the 0, isn't it? So if we multiply by n, we're going to get 0 times, and then we're going to reduce the power by n, but it doesn't really matter what we do because we've got 0 times anything is going to give you 0, isn't it? So let's just review what's happened. We started with x squared and we differentiated it once and we got 2x. Then we had x to the power of 1, or x. We differentiate that and we get a constant. And then if we differentiate a constant, we'll just get 0. Is everybody okay with that as far as it goes? Right, so what I want to do now is differentiate a polynomial. So we can say, for instance, y is equal to 4x cubed plus 3x squared minus 6x plus 5. Okay, so now what I'd like to do is to get dy by dx, and we're going to do this term by term. You can do polynomials term by term. We're going to multiply by the 3 here, so we're going to get 3 times 4, that's going to be 12x, and then we reduce the power by 1, so that becomes 12x squared. Okay, now we get the next term. We're going to multiply 3 by 2, so we're going to get 6, and then we reduce that power by 1, so instead of x squared it becomes x, and then we're going to get the next term. This is x to the power of 1, so that's just going to give me minus 6, because minus 6 times 1 is minus 6. Then we're going to reduce the power by 1, so it's going to be x to the 0, and we may as well just leave that as 1. And then we've got a constant term at the end here, which is at 5 times x to the 0, if you like. Then we multiply by the 0, so that term will disappear. Okay, so I'll just remove that. Now, can I give you a couple of minutes, not even a couple of minutes, to differentiate this quantity again? So I would like to do d by dx of dy by dx. Okay, and yeah, okay, thanks Ahmed. So anybody disagree with Ahmed? What we're going to get is 12 times 2, so that's going to be 24. We reduce the 2 by 1, so that's going to be 24x, and that's that term dealt with. This is 6 times x to the power of 1, 6 times 1 is 6, x to the power of 0 is 1, so we get 24, 24x plus 6. Okay, any questions on that before I move on? And this power here, 3, it could be 27 for all I care. It could be 58. It could be any power you like. Right, now then, what I'd like to do is imagine that we've got u. What about minus 6? Thank you, Ian. I'm not going to answer your question just yet. I do plan to do it, but not yet. I'm going to say u is a function of x. Okay, yeah, I will come back to it, I promise. U is equal to a function of x, and v is a different function of x. Let's call it function of x1, one function of x and the other. So u is a function of x and v is a different function of x. Okay, now if I would like to differentiate d by dx of u times v, okay, so now what this means is it could be one function of x, like e to the x or something like that, and the other function could be sine x. So you could have something of something like e to the x sine x, or x plus 3 brackets sine x, or something like that. So if you get something like this is called a product, and we're now doing something called the product rule, and the differential of this is u times dv by dx plus v times du by dx. Okay, so that's a product, and that is the product rule. So u and v is a product, and this is how you calculate the product. So what I'd like to do now is have an example of that, and what I'm going to do is say that u is equal to 3x squared minus 2, and v is equal to I don't know, 4x squared plus 5. Right, so now I'd like to do d by dx of uv. So that's going to be 3x squared minus 2 brackets 4x squared plus 5. Okay, so we'll do this in the way that I've written here. So we've got u, which is 3x squared minus 2 times the differential of this bracket, which if you look at it is going to be 8x. Okay, everybody see where the 8x came from? And then I'm going to add to that v, which is 4x squared plus 5, and I'm going to multiply that by 6x, okay, which is the differential of the first bracket. So I'm now going to tidy that up a little bit, and I'm going to get 24x cubed minus 16x plus 24x cubed plus 30x, which is going to equal 48x cubed plus 14x. Okay, everybody happy with that? Now what I'd like to do, yeah, thank you Ahmed. Now what I'd like to do is to expand these brackets. So 3x squared minus 2 times 4x squared plus 5 is going to equal 12x to the 4, and then I'm going to get plus 15x squared minus 8x squared minus 10. Is that right? 12x to the 4, 15x squared minus 8x squared minus 10. So that is going to equal 12x to the 4 plus 7x squared minus 10. Okay, can I give you a couple of minutes to differentiate that expression? I say minutes, I mean a few tens of seconds to differentiate that expression. Okay, so we're going to do, thank you Mohammed, we're going to do the first term, so we're going to multiply 12 by 4, so that's going to give me 48x, and then we're going to reduce 4 to 3. Okay, then on the next term we're going to multiply 7 by 2, so that's plus 14. Then we're going to reduce the 2 to 1, so it's just going to be 14x. And then the final term is a constant term, so that's like 10 times x to the 0, so that means that that becomes 0. So just to review then, what we did in the first instance is we used the product rule to differentiate that, and that's the answer that we got. And in the second case I expanded the bracket, so I didn't need to use the product rule, so I got this polynomial. We've differentiated the polynomial and they are the same. So the fact that those two are identical just confirms that the product rule works. Okay, are there any questions about what I've just done there? That's the product rule that we've done. So either way is acceptable to use. Yes, Ruben, that's absolutely right. Either way is acceptable to use if you can use it. In general terms, this is going to be e to the minus 3x or something, and this is going to be sine x or something of that sort. So it's generally speaking, you're not easily going to be able to use either. Yeah, that's true in that case, but as I say, in most cases that's not going to be the case. Right, I need to mention, so that's the product rule. I need to mention the chain rule. So this is the chain rule. Let's go back to my black pen. So the chain rule says that if y is a function of u, y is a function of u, and u is a function of x, okay, then we can say that dy by dx is equal to dy by du times du by dx. Okay, so that's the chain rule. I'm just mentioning it here. I will use it in a minute, but I'm just going to need it a bit later on. But we've got it written down, so I can use it. No, I can use it here. So why don't we say, so for instance, if y is equal to 3x squared minus 5 to the power of 4. Okay, that's an example of the chain rule. So what Ruben was just saying is, can we expand the brackets? Well, you can just expand the brackets, but look, I'd have to do this 4 times. So I'm going to get a term of x to the power of 8, aren't I? But if I say let u equal 3x squared minus 5, okay, so now what I can find out is du by dx, so du by dx is equal to 6x. Everybody okay with that? I've multiplied by the power and then reduced the power by 1 and the constant term disappears. And then dy by du, so y, we're letting u equal that, so y is equal to u to the power of 4, isn't it? So dy by du is equal to 4u to the power of 3, isn't it? Okay, so therefore dy, that's not a very good y, let's try and make a better y, dy by dx is equal to 4u cubed, so I'm just going to put u in here, so it's 4 brackets 3x squared minus 5 cubed times du by dx, which is this 6x that I've got here, 6x, like that. So obviously you wouldn't leave your answer like that. You'd say that that is equal to 24x brackets 3x squared minus 5 cubed. Okay, and that is the differential of that. Now, what we could have done if we were mad is we could have expanded this bracket, then we could have done it term by term, and then you could have collected common terms, and this is where you'd have got to. All right, so that's an example of the chain rule. And then we need to look at the quotient rule. And this is the worst thing you're going to find in differentiation. What I mean by that is it doesn't get worse than this. So what we've got is u is a function of x, u is equal to one function of x, and v is equal to another function of x. Thanks, Timothy. This is the quotient rule. Okay, that's the quotient rule, and what we want is y is equal to u over v. So dy by dx is equal to, and this is the rule, it's v du dx minus u dv dx all over v squared. Okay, and that's the quotient rule. Just so you know, the product rule, the quotient rule, and the chain rule, I give you all of those on your exam on the equation sheet. So you've got all of these. You don't have to memorize them, though, to be honest, if they stick in your head naturally, then it's quicker than having to look them up on the equation sheet. Okay, let's do a quick example of that, shall we? So I don't know, let's say y is equal to 5x minus 3 over 2x plus 4. Okay, so dy by dx is equal to, right, so let's see what we've got to do here. So it's v du dx, so v is 2x plus 4, so there's v, and du dx is just going to be 5, isn't it? And then I'm going to be minus u, which is 5x minus 3 bracket times dv dx, which is just going to be 2, and that's all divided by 2x plus 4 squared. Okay, you wouldn't leave it like that now, would you? We're going to get 2x times 5, which is 10x. Let's write it out. So I'm going to get 10x plus 20. And then on this one, I'm going to get 2 times 5x, so that's going to be minus 10x. And then I've got minus times minus 3, so that's going to be plus 6. Okay, and that's over 2x plus 4 squared. So that gives me the final answer of 26 over 2x plus 4 squared. Okay, and that's the quotient rule. Right, I think that's probably a good place to stop because we've covered quite a few rules there. This is sort of pure maths at this point, and what I'll do after the break is I'll go into applying this to particular types of problems. So unless there are any questions now. 20 minus 6, no, it's not 20 minus 6. Good question though, Timothy, because we've got minus times minus. And yes, Francis, this session is being recorded. Yeah, so we've done 3 rules there, and they are all in the textbook. What we'll do now is we'll break into the rooms. We'll go over the questions that are on these 3 rules, which is the product rule, the chain rule, and the quotient rule. And then we'll come back and we'll actually apply these to some real things. Okay? Is that like a change of speed? Yes, Robin. Let me just go over that. That's what I was trying to do earlier. If you've got a distance, which is a distance x, and you calculate the rate of change of distance, that gives you speed, doesn't it? So if the distance is 100 miles and the time is 5 hours, the rate of change of speed, the rate of change of distance is the speed. That's 100 miles an hour or whatever it happens to be. If you then differentiate the speed, that's to say you put your foot on the accelerator and you're going faster, so your speed is changing, the rate of change of speed is the acceleration. Okay, we know that. That's stuff that we do all the time. But if you think about it, speed is the rate of change of distance, and acceleration is the rate of change of speed, which means that acceleration is the rate of change of the rate of change of distance. That's a weird sentence to say, isn't it? So acceleration is equal to, and this time I'm going to say d by dt, which is the rate of change with respect to time, d by dt of x. So the rate of change of x, which is your length, the distance, is speed, and the rate of change of speed is acceleration. So when I was just learning this, in year 8 or 9 or whatever it was, they say that the acceleration is meters per second, don't they? And I used to think, what the heck does that mean? How can you have meters per second? What does it even mean? And then when you start doing this, you think, okay, this is the rate of change of distance, so that's meters per second. and this is the rate of change of speed, which is meters per second and you can carry on. You don't have to stop there. You can have the rate of change of acceleration if you want, but so yeah, the rate of change of distance is speed, and that's sort of what differentiation gets us. Okay, enough of that. I will stop sharing my screen